We now look at the analysis of this algorithm. We want to claim that if you randomly shuffle this line segments that we use in this incremental algorithm, then the expected query time will be log n. To do that, we first see what does expected query time mean. So expected query time, so here we're going to do the expected query time for one fixed query. So in other words, the way we assume is the following, that we assume that before the algorithm starts, we pick one query that we're going to ask, and then we look at the random shuffling of the permutation, the random permutation of the line segments, and then we analyze the query time of this particular query value, query point that we have picked. Since the algorithm itself, it doesn't care about which query we pick, in other words, oblivious to which query point we're going to ask, this makes sense to consider a fixed query that has been selected before we run the algorithm or we pre-process the segments. Okay, so in this view, if you pick one random query, let's say you pick, this point Q over here, then the query time of this point Q is the length of this path. So for example, in this particular structure, the length of this path will be 3 or 4, depending on your, well, let's say it's 4, right? Because you compare with S1, it is below, so you follow this node for this fixed query. Then you compare with S2, it is above, so you follow the above pointer of the second segment. Then you compare with S3, so this is below, right? And takes you to region K, and you pass through 1, 2, 3 internal nodes, and you end up in a leaf, so we can say the query time is 4. So the query time is essentially the depth of the path it takes for your query point to reach a leaf in this structure. And the expected query time is the average query time over all n factorial possible permutations. Okay, so this is essentially what it means. And as we discussed, it's the length of this path. So what we can write here is that the expected query time is the expected length of the path. Then we can create a random variable xi, and this is defined in the following way. We say xi is 1 if when we insert segment si, a new node is created on this path. So remember that this the definition of xi is with respect to the query point q. So since we have fixed the point q, this makes sense. And based on this definition, the length of the path is the sum of the xi's. This is because if a segment does not create a new node on the path, then the xi is 0. If it creates a node, the index xi is 1. So therefore, the length of the path is essentially the sum of the xi's, whether the I segment creates a node or not. So since it's the sum of the xi's, by the linearity of expectation, if we again remember, we could swap the order of the summation and the expectation, which means that this equals the sum of the expected values of the xi's. Okay? But xi is a 0, 1 random variable, which means, in other words, it's either 0 or 1. So therefore, the expected value of xi is basically just the probability that xi is 1. We can basically follow this by the definition of the expected value. So what is the expected value of xi? Xi has only 2 possibilities. So this is the probability that it is 1 times the value of xi, which is 1, plus the probability that is 0, 1 minus pi, times the value of this random variable, which is 0, so times is 0. So and obviously this part cancels out, so we are only left with probability that this xi is 1. So for a 0, 1 random variable, the expected value will be essentially the probability that it is 1. Okay, so we have that thing, and then we just need to argue about the probability that the ith segment creates a new node on this path. And then we could use the following observation that we again used in the previous backwards analysis. We could say that the probability that Si creates a new node is essentially equivalent to the probability that the line segment that we're adding intersects the old region where the query point lied to. So to visually see this, let me go back to the previous slides. Let's say this picture. Okay. So here, these CDE are the old regions. If the query point is here, then the average depth will be increased. This is because E will be replaced by the segment S3, and then we'll have one more leaf down there. But if the query point is over here, then I'm not touching the region G after I insert S3 in this picture. So therefore the length of the path won't increase at all. So it is very clear from the way this algorithm works that the length of the path increases by 1 if and only if the query point is inside one of the old regions intersected by the segment SI that we're adding to the picture. Okay, so that part again follows from the way this algorithm works, and then we're going to get to the backwards analysis part. Because this is essentially equivalent to the property that the trapezoid must be adjacent to SI. So the new trapezoid that is created should be adjacent to SI. And this can happen in one of the possible cases. Okay. Okay, so to see this, we can use the backwards analysis, right? Because so let's say this is a new trapezoid created after I have inserted SI. And let's assume that I have fixed the segments SI plus 1 all the way to Sn. So I have only segments S1 up to SI plus 1 left. I'm going to go over this quickly because it's very similar to the backward analysis that we did before. Okay, and let's say the query point is inside this trapezoid. If none of these segments is SI, then adding or removing SI has no effect. Then it means that SI is somewhere else in the picture, and therefore if I remove SI, nothing happens. But if one of these segments is SI, then removing SI will actually change this region. It would mean that in the old so that it means that query was inside an old region that was intersected by SI, and once I add SI, the length of the path increases by 1. And by backwards analysis, the probability that SI is this top vertex is 1 over I. The probability that SI is the bottom vertex is 1 over I. The probability that SI is this is on the right hand side is 1 over SI, and the probability that it's on the left is also 1 over SI. So therefore, the probability that the new node is created when we insert SI is essentially at most the summation of these probabilities, which is 4 over SI. And then we can plug this back in. We calculate that this probability is 4 over SI, so the expected value of Xi is 4 over I. Then we plug it in, we get essentially this upper bound for the expected length of the query, which is 4 times 1 over I. And if you know your basic formulas, 1 over I is, sum of 1 over I is a harmonic series, which is roughly equal to log n. So we could say that 4 times h of n is O of log n. And that concludes the expected query time of this algorithm.